number 12, integral from 0 to infinity, e to negative x squared over x squared dx. This is honestly probably one of those problems the professor probably put on his exam to differentiate who gets the A's from the B's, because there's a very subtle detail here. Most people would recognize that this is an improper integral because the upper limit is infinite. However, this is a double improper integral because this lower limit makes it improper as well. We would be dividing by 0 as x approaches 0. So you have to set this problem up properly. You'll see why, for those people that didn't pay attention, that this was a double improper integral because of that. As I said, most people would only recognize it as improper because of the upper limit. They'll think it converges, but actually this integral diverges. So let's explore carefully why that's the case. So we got to split this integral up. It's doubly improper, so let's make it improper on one end only by setting up two integrals in which each of them are improper on one end only. So we can just break up to, for example, 0 to 1, and then 1 to infinity. Okay? And then here's the limit notation if your instructor, grader, professor, whoever requires it. Okay? We got to evaluate one at a time. For this integral to converge, the original guy, both pieces need to converge. If even just one of them diverges, the whole thing diverges. Okay? So if we evaluate the second part first, this is probably the easier part. Let's do a comparison test. I can rewrite e to negative x squared of x squared. Instead of a negative exponent, to make it positive, I move it to the denominator. Okay, so 1 over e to x squared times x squared, all on the bottom, is less than or equal to 1 over x squared for x is greater than or equal to 1. Okay, we're going to be dividing by something bigger. So that's why our value, final value, is smaller. Okay? And we know that integral from 1 to infinity, 1 over x squared dx converges. Hopefully you know that by now. This is a very common one we compare to. Since we know this converges and our thing's even smaller, then by comparison test, our integral converges as well. So most people would say, oh, we're done. And thus it converges. And then the grader, professor, whoever is scoring the exam will mark you wrong. We have to check this integral as well. Or this one, same thing. Okay? So to check the convergence of this piece, we can do another comparison test. Okay, so same algebra as before, negative exponent, I write it as positive exponent by moving it down. Okay, you got to set up your comparison a little carefully here. This one's a little trickier. So within this interval 0 to 1, our function is greater than or equal to 1 over e times 1 over x squared. How did I think of that? Well, the key is we're restricting it in this interval from 0 to 1, okay? So it'll be e to some fractional power, because x is between 0 and 1. For example, a third, half, a fourth, an eighth, so on and so forth. So when it's a fractional power, the fraction is less than 1. It's like, for example, if this x squared was equal to half, we would be square rooting. If x was half, then it'll be e to the 1/4, right? So we'll be fourth rooting. So when we fourth root e, it's going to be smaller than e. Hopefully you would agree with that, right? Or square root e, it's smaller than e. So when it's smaller at the bottom of the fraction, the final value is bigger. Okay, this is the hard part for setting up these comparisons. We got to pick something properly. So I decided this function, okay? And this function I know diverges from 0 to 1, but we could quickly show that. 1 over e integral from 0 to 1, 1 over x squared dx. We take the limit. It's infinite. Okay? Therefore, since this guy diverged, the whole thing diverged. The original integral diverges as well. Okay? So once again, let's go back to here. Okay? Most people would just have bothered with this. And they'll determine the convergence, that this guy converges because this guy converges. But they missed this whole piece over here. This is actually divergence, as we just saw. This is infinite plus something finite is still infinite. So our original guy diverges. Again, this is probably intentional of the professor to pick this problem on one of his exams, and it's a very typical strategy for professors to decide what to put on the exam because they need to differentiate who gets an A versus a B versus a C and all that. So they pick problems like this where most people would probably not have realized that this zero makes it improper and actually is the limit that makes it diverge. The limit of integration that makes this diverge. Okay, hopefully you got the point of this problem. Be careful when dealing with improper integrals. You have to check if both limits make it improper. You'll see that sometimes it diverges. One of the pieces diverges, so the whole thing diverges. If it converges, both pieces need to converge in order for the original guy to converge. All right. Hopefully this is helpful. Hopefully this is insightful if you are practicing and studying for an exam yourself. Please give this video a like if you did find it helpful, and feel free to subscribe to the channel as well to check out more videos like this.